Hi.
Hi.
Hi,
Yes,
everybody.
sir.
My name is Russ Perkins. I'm a PhD student at UMass Lowell. I work with my lab mate, Zara Kavas, and my instructor, Paul Robinette. We do primarily trust research right now, and this is kind of, I'm relatively new to the field. I'm an electrical engineer, originally signal processing, so modeling signals now, trying to model people. So this is basically the what I've noticed and kind of the questions that we have, because we do a lot of trust research. It was during the pandemic, so a lot of the research was done with mechanical Turk participants, and you find out that the data is kind of noisy, right? Because people mechanical Turk operate in certain ways, and they have their own way of doing these problems. And I guess my question is why? It's not enough to me to say, well, they just do, and then we clean the data. I'd like to know why and see if we can figure that out. So what I'm going to go over here is a little bit of utility theory. I'm sorry, I completely forgot the title. The title is predicting irrational human behavior, right? Because people tend to act irrationally. It's something everybody's familiar with. I'm just interested in how we can use that to maybe understand what a person is going to do. So little overview of utility theory. Going to go a little bit over how people process information, at least theoretically, and then what we've studied so far and some observations that we've made, and then a little bit into future work. So some things for this presentation. This is a happy robot. This is a mad robot. This is a happy person. This is a sad person, and my favorite is this is the who cares person. All right, so like I said, I'm an electrical engineer, so I'm legally obligated to have some type of equations in here. But basically, just really quick, utility theory deals with the prospect X, something that you're going to get, a probability P of which you're going to get that. So then the utility is kind of how much it matters, right? So the overall utility is big U, and then the utility of each one of those prospects X is little u. And so the overall, the big utility, the overall utility is going to be the sum of the probabilities of the utilities of each prospect, and then more importantly, an asset that you add to your utility, when you add it, the overall utility needs to be greater than the utility of that asset itself. And then what else is it? It's a rational model, right? So A is greater than B, B is greater than C, so A therefore must be greater than C. The only problem is that even though we use this to kind of model decision analysis, people don't necessarily make those decisions that way. Just as a little example, I don't know how many people are familiar with this, but this is called the ultimatum game. So we have two participants, Mr. Star and Mr. Square. And somebody gives Mr. Star $1,000. The condition on that is he needs to share some of that with Mr. Square. So he'll say, I'm going to give $100 to Mr. Square. And then the problem is that $100 is more money than Mr. Square had to begin with. So originally his utility is $0, now it's $100. But he's going to say no because it's unfair. So that cancels. My animation got a little messed up. I apologize for that. It was working fine in the preview. So even though utility theory says that Mr. Square should take that $1,000, the $100, I'm sorry, he doesn't, because it's unfair, right? So it's not a rational decision. And so why do people make decisions like that? So I mean, first, we're loss averse, right? So I mean, if you look here, we're more fearful of losing things than we are of then we're hopeful of gaining things. If you take a look at the slope, right, the slope for loss is much greater than the slope for gain. We're also poor judges of probability, right? So You know, you see this in lottery, like a small increase in the purchase of lottery tickets, like to 100 in people's minds, you know, greatly increases their chances of winning the lottery. And then finally, we use heuristics to solve problems. So the heuristics that we're going to cover here are availability and representativeness. There are two more that I'm not going to cover, but they help us by reducing mental efforts, and they simplify difficult problems. They're quick, and they help with our problem solving. So the first is availability heuristic. So we have a set A, and then there's this subset B, and A, let's just say, is all of the information that exists about something, and B is the available information to a person, right? We know that B is contained in A, and therefore A is greater than B, but let's say that this is B is the information that's available to a person making a decision, and that B is weighted by the tragedy of airplane accidents, right? So which is more dangerous? Well, numerically, many more people are endangered by automobile accidents. But since the information is weighted to the available information to people is weighted toward the dangerousness of plane crash, people think that plane crashes are more dangerous than cars. People get into cars every day, and there are people that won't fly. Then we get into stereotyping and the representative heuristic. So the representativeness is how we categorize. We generally categorize information. So we take it and we see stuff. And so right here, two images that we don't really need explaining, right? So the smart science type and the strong dumb type. Right? These things are categorized, so we don't have to do much information processing. But how does this apply to robotics? So we can see here, this is a robot, and it's looking at a person and has learned that, okay, if I see a firefighter coat and a firefighter hat, right, I can shortcut my learning process by associating that outfit with this axe. And what these strategies for representativeness do is they actually help the robot to make decisions kind of like we make decisions. So you can bootstrap a learning process to learn information about to learn something about a new person, and then you can use these stereotypes that you've created for feature selection. The problem is, of course, stereotypes can run afoul, so we constantly need to be careful about where our what information that we're processing. And this, I guess, ties into the explainability of our models, right? We need to know why people or why the robots and the models that we've programmed with are making this type of information. Just touching a bit more on stereotyping. So the stereotype content model. This was kind of developed as part of social cognitive theory and some of Susan Fisk's work on the social content model. But this is a paper written by Brian Reeves, and it basically asks people to categorize robots in the with respect to warmth and competence. So competence here is on the x-axis, and it goes from low to high, and then the y-axis is warmth, low to high. This is a model that is used. It's called the stereotype content model for people, because when people are applied to this, right, you can emotions about these people associated with the axis are, you know, high competence, high warmth is for helping, but low competence is neglecting. And it gets even more complicated when we talk about these axes: pity, admiration, envy, and contempt. The question that I have in reading about this and reading about social cognitive theory is if people can place these robots in these places, are these robots going to elicit the same type of emotion? And if they do, or if it's some different emotional.
Sorry, Russ, I accidentally muted you right in the middle of the sentence.
Okay, great. All right, no problem. We'll see if I can pick back up where so if there is an emotional mapping similar to this based on the stereotype content model, then a robot, just by understanding its place, what its warmth is, what its competence is, can use the representative heuristic to determine how somebody is going to feel about it or what emotions it is going to elicit. All right, so on the trust research we have been doing, I'm going to take you through kind of a game and then show you how we're trying to take a look at this and see how we can determine what type of a reaction somebody is going to have through a stimulus. The idea being, if we can understand how things act irrationally and we can provide a stimulus pertaining to, let's say, the availability heuristic, we can then determine that the person is going to say, hey, I'm more scared of planes than I am cars, because we understand that process. So we play a search and rescue game with a simulated robot and a human player. Before they play for a couple rounds and they collect targets. Before a user sees any of the scores that the robot gets, they choose to integrate or discard it. So the target types are a star, which is 100 team points. So this is a team game. Circle is negative 100 team points. And then we added these triangles. So these triangles are meant so that people and robots can deceive each other or be counterproductive to their partner. So the triangle is gives you 100 individual points and it takes away 100 team points. And these games last anywhere from 10 rounds to 13 rounds, and you know, the robot operates autonomously from the person, and at the end they you know, the robot says, this is how much I found, and prior to that the person has to say whether they're going to accept it or not. But during this process we've applied interventions such as apologies, deceptions, and explanations to try to calibrate trust, right? So how can I change the perception, your perception of what I'm doing based on an intervention? And it looks like, although none of this is published yet and we're still processing this, that you can provide a stimulus to somebody and have them act a certain way. So if you can do that, then you can probably apply it to these irrational heuristics, by saying, I'm going to do something, and then since I know you're going to act in a certain way that is irrational, I can predict what you're going to say. We use a little bit more theory, some interdependence theory. So basically this kind of allows us to quantify risk. And the reason we do this is that we can say that trust is proportional to the risk. So the loss is going to be what happens if you integrate on a good thing versus what happens if you integrate on a bad thing. It's going to be the difference between those. So the maximum difference here is going to be 12. And so we can kind of define this risk thing, and we can figure out what the trust is going to be. The problems with this model is then again figuring out what these outcome values are supposed to be. I mean, here they're 6, -6, but how do we figure out those? And it goes back to what we talked about. When people make decisions about risk, they are much more risk averse. They're much more risk. Much more worried about losing something than gaining something. So we can use those types of irrational models to apply to these outcomes to create a more predictive model. This is one other thing we noticed that was kind of interesting, and we're going to be doing follow-up experiments on this. Is that when a robot starts to do something like pick those pink targets that we talked about, the person starts picking pink targets back, right? As even though what they're doing is counterproductive to their score, right? So they're doing something that's irrational because they perceive this negative intent from the robot. And even when we introduce this concept of this negative intent, people automatically think, or I'm sorry, people may think that even since the capability of that robot is there to attack them, to give them a negative, to reduce the team score and do something selfish, that the robot can increase his personal score, they'll just start right off the bat acting irrationally and attacking the robot by picking their own pink scores. Just a little bit going into future work here. I mean, what I think I'd like to focus on is trying to model these heuristics, trying to do experiments on them and create some type of models for them using theories from behavioral economics. We talked about prospect theory a little bit, and then marketing strategies, which I think they use heuristics to determine human behavior, and then following it up with social cognitive theory that we talked about with the stereotype content model. Are there any questions? Thank you very much.
Thank you. Yes, are there questions? Let's see. Does not look like you're going to have.
I'm okay with that.
Yeah. I think we're also okay with it, given the that we're running behind the schedule. So I'm pretty sure it will make Arkady happy if we can catch up a little bit on time. So I think that ends then the first part